Hey guys, so in this video we're going to walk through the process of cellular respiration. We're going to talk about how glucose makes ATP, and we're going to follow every single major step, tracking our carbons and keeping an eye on how much ATP is actually made. So if we take it one step at a time, we're going to be able to see how everything fits together. So to start, we begin with glycolysis, and the starting product of glycolysis is glucose. Glucose is a 6-carbon sugar molecule. Its formula is C₆H₁₂O₆. Glycolysis, it takes place in the cytosol, and it's that first stage of cellular respiration. Glycolysis is going to take one glucose, which has 6 carbons, and turn it into 2 pyruvate molecules that have 3 carbons each. So we have 6 carbons and 2 pyruvates that have 3 carbons each. We have no loss of carbon. All 6 are accounted for. So in the first half of glycolysis, we call this the energy investment phase. And that's because we use 2 ATP and turn them into ADP to release energy to prepare for the breakdown of glucose. In the second half, we call it the energy payoff phase. We're going to make 2 NADHs because we're going to take 2 NAD pluses and reduce them into NADH and a hydrogen ion, or a proton in other words, and we're also going to make 4 ATP. This is because our energy payoff phase, it happens 2 times. So for glycolysis, we have an ATP total of 4 made, but we used 2 in that first energy investment phase. So we only netted 2 ATP. We also created 2 NADH and our final molecule product, which are 2 pyruvate. Each NADH, it can carry 2 electrons. So next, we have pyruvate oxidation. The 2 pyruvate that we made from glycolysis, they're going to move into the mitochondrial matrix from the cytosol. Each pyruvate is going to undergo a conversion step called pyruvate oxidation. Oxidation of pyruvate is going to link glycolysis to the citric acid cycle. We do not make any ATP in pyruvate oxidation, so it is not a step cellular respiration. It is an intermediary between glycolysis and the citric acid cycle. So for each pyruvate, we're going to have 1 carbon removed into the system as carbon dioxide, and we're going to reduce 1 NAD plus, 2 NADH, and a hydrogen ion. And that remaining 2 carbon unit is going to become acetyl-CoA. So we start with pyruvate, we get a carbon removed, and we end up with acetyl-CoA. So because we have 2 pyruvates, we're going to have a release of 2 carbon dioxides, 1 from each pyruvate, 2 NADH produced, and 2 acetyl-CoAs. Our acetyl-CoAs, they have 2 carbons each. So to check, we started with 6 carbons in glucose. We released 2 as carbon dioxide. So we now have 4 that remain in between 2 acetyl-CoA molecules. So we still have all 6 carbons accounted for. And this brings us to the citric acid cycle. Each acetyl-CoA is going to enter the citric acid cycle, and we also call this the Krebs cycle or the tricarboxylic cycle, or TCA for short. This cycle is going to happen 2 times per 1 glucose. It happens 1 time for each acetyl-CoA. In each turn of that cycle, the 2-carbon acetyl-CoA is going to combine with 4 carbon molecules to make citrate. And through a series of reactions, 2 carbons are going to be released as carbon dioxide. We're going to reduce 3 NAD pluses into NADH. We're going to get 1 FAD molecule and turn it into FADH₂. FADH₂ is also a high energy electron carrier that can carry 2 electrons. And we're going to produce 1 ATP or GTP equivalent. But because we ran that cycle 2 times for 1 glucose, we're going to release a total of 4 carbon dioxides, 2 per cycle, 6 NADHs, 3 per cycle, and 2 FADH₂, 1 per cycle, and we're going to create a total of 2 ATP or GTP, 1 per cycle. So to check our carbons, we have the 4 remaining carbons, 2 from acetyl-CoA, and all 4 of those carbons, they were released into the system as carbon dioxide. So all 6 original carbons from glucose, they are now accounted for. So far, we've only made a total of 4 ATP. We made 2 net from glycolysis, and we made 2 from the citric acid cycle. But the real energy payoff is going to come from the electron transport chain, which is located in the inner mitochondrial membrane. all of our NADH and FADH₂ that we have produced so far, they are loaded with our high energy electrons. Glycolysis produced 2 NADH, pyruvate oxidation produced 2 NADH, the citric acid cycle made 6 NADH and 2 FADH₂. So in total, we've made a total of 10 NADH and 2 FADH₂s. Each NADH is going to donate 2 electrons to complex 1, and each FADH is going to donate its electrons to complex 2. As our electrons pass through the complexes, we're going to have hydrogen ions, also known as protons, pumped from the matrix to the intermembrane space. This creates a proton gradient because now we have a lot of protons outside in the inner membrane and fewer protons inside of our mitochondrial matrix. Those electrons, after they've passed through the electron transport chain, they're eventually going to combine with oxygen gas and hydrogen ions to form water. And that's why oxygen is so essential. It is electronegative and it's going to cause those electrons to come closer to it. It is our final electron acceptor. So now that we have that proton gradient in place, our hydrogen ions, they want to naturally flow back into the matrix, but they can't do that on their own. They need help to diffuse down that gradient. So they do it through ATP synthase, which is an enzyme. As our protons pass through ATP synthase, it's going to spin like a turbine and it's going to join ADPs with inorganic phosphates to make ATP. This process, it is called chemiosmosis, and together with that electron transport chain, it's part of oxidative phosphorylation. So oxidative phosphorylation, it is an umbrella term that is going to encompass the first part, which is the electron transport chain, and the second part, which is chemiosmosis. Remember that the electron transport chain, it does not directly make any ATP. It is only going to set up that proton gradient so that chemiosmosis can create ATP. Oxidative phosphorylation is going to create the most ATP in all of cellular respiration, making about 28 per 1 glucose. So now we're going to summarize the total energy that was harvested only from 1 glucose. Glycolysis, it netted 2 ATP, and we had 0 carbons released. Pyruvate oxidation, it does not make any ATP, but we did lose 2 carbons. And the citric acid cycle, it made 2 ATP and we lost 4 carbons. When we got to oxidative phosphorylation, we made about 28 ATP, but we didn't use carbon the way that glycolysis and the citric acid cycle do. We used the electrons that we harvested from glycolysis, pyruvate oxidation, and the citric acid cycle. So we made a total of about 32 ATP per glucose molecule. And remember that all of the carbons from glucose, all 6 of them, they got released out as carbon dioxide. And that's the process of cellular respiration. We take 1 glucose molecule and break it down over and over again to make about 32 ATP. And we can track every single carbon along the way. If you have any questions or you need a breakdown of a specific part, drop a comment below. Thanks for watching, and I'll see you next time.